What if I told you that building the world's highest railway bridge required conquering not just extreme weather and treacherous terrain, but also the very laws of physics? This is a place no human being was ever meant to go. Deep in the foothills of the Himalayas, temperatures near the Chenab Bridge site fluctuate wildly, plummeting from a scorching 50 degrees Celsius down to freezing. Everywhere you look, jagged cliff faces carve out deep, dangerous canyons. Imagine the immense challenge for crews attempting to construct a record-breaking bridge here. Accessing civilization requires trekking dusty tracks on foot or embarking on a boat journey along the river. Simply reaching the Chenab Bridge site was an enormous undertaking, let alone maneuvering the 30,000 tons of steel needed for its construction. With no motorways, no nearby factories, and not a single flat, stable surface in sight, this is construction in one of Mother Nature's most unforgiving environments. It might sound cliché, but sometimes cliché ring true. Constructing the Chenab Bridge should have been impossible. From searing temperatures to perilous ice and snow, working conditions truly don't get much tougher. And it's not just the crews who suffer. When exposed to such extremes, steel can expand and contract, making it incredibly difficult to manipulate and accurately align. But while crews battled the elements, an even greater challenge loomed: the wind. This canyon can experience gusts of up to 265 kilometers per hour. That's unbelievably dangerous for people working hundreds of meters up in the mountains, especially when maneuvering thousands of tons of steel into place. And even if the weather above granted a reprieve, there was no guarantee an earthquake wouldn't shake the ground to its core. Any one of these factors alone could have halted the entire notion of building a canyon-spanning bridge in this location. Yet they all pale in comparison to the Chenab Bridge's primary hurdle: simply getting to the construction site. David Mackenzie, Senior Technical Director for COE, has been involved with the project since 2004. He recounts, "When we first started the project, we were invited to go up, and donkeys were provided to help us ascend the stream. On the first trip out, we took a boat because it was quicker down the river than trying to negotiate these treacherous mountain paths. But why build such a colossal structure in the first place? Imagine you're in Jammu and need to travel to the Kashmir Valley. These regions are separated by mountains and connected by one main artery, National Highway 44, which is frequently blocked by snow. This is where the Chenab Bridge comes in. It's an impressive section of India's new 169-kilometer all-weather rail line, cutting quite literally through the mountains. And as if the weather conditions weren't challenging enough for the construction team, not everyone supports this new route. Kashmir is an area of high political tension and one of the most militarized zones in the world, divided between India and Pakistan. Both claim territory in the region and administer different parts of it. While India asserts its new all-weather rail line will provide an economic boost and improve travel connections, opponents claim it's being used to exert more control over the region. Despite these concerns, construction of the line has pushed forward. In total, this massive undertaking features an incredible 943 bridges and 36 tunnels, one of which is 3 kilometers long. Reports suggest this monumental endeavor will cost around $5 billion. To put that into perspective, in New York City, $5 billion would only fund about 2 kilometers of the 2nd Avenue subway, when seemingly every project we examine costs millions, if not billions of dollars. It's easy to lose perspective over the immense sums involved. Billions for a skyscraper here, billions for a railway there. Sometimes these projects even run into the trillions. Balancing those budgets would give most of us a cold sweat. With the sheer scale of the challenge in mind, let's return to the Chenab Bridge itself. This is the Chenab Bridge worksite in 2020. On either side of the canyon, you'll notice fabrication workshops. These are unusual on modern construction sites. Typically, for a project of this magnitude, key components would be prefabricated in distant factories and then transported to the site. But as we've established, that wasn't an option here. So, how did they get 30,000 tons of steel up there? The answer is truly extraordinary. To make this remote location even remotely accessible, 26 kilometers of roads were specifically built for this project. If you're prone to travel sickness, you might want to look away, as these roads were constructed in precarious locations, clinging to mountain sides and traversing serious cliff edges. David Mackenzie explains, "The most efficient way of transporting steel is in flat plate. Think of it as an IKEA catalog. Everything came to site flat-packed, and indeed all the cutting and all the drilling was done on site. Don't expect things to get much easier once the materials have arrived. With all the components finally on location, the next daunting task is building the bridge hundreds of meters above the ground, spanning a colossal canyon. The topography here is nothing short of a nightmare. A jagged, rocky canyon split by a river offers breathtaking views but presents an incredibly tricky engineering challenge. As mentioned earlier, one of the biggest factors is the wind, thanks to a phenomenon known as the Venturi effect. This occurs when a narrow passage, like a canyon, effectively becomes a giant funnel. As wind passes through, its pressure drops, and its speed increases, creating powerful and chaotic patterns. And that's all before considering the terrain. Geologically, the Himalayas are very young and still moving. The range was forced up by the Indian and Eurasian plates colliding, creating a heavily twisted landscape. The rock along its canyons is fractured and friable. By nature, a canyon is often V-shaped. The problem is, if you fix a tower to one side of that V-shape, particularly a side with very unstable rock conditions, there's a tendency for that tower to want to slide down the valley. This is precisely why the Chenab Bridge employs an arch design. It begins from either end, with both sides meeting in the middle, creating a locked formation. As they converge, the two sides push against each other, forcing their weight down their legs into the sides of the mountain. Given that a canyon acts like a wind funnel, generating powerful gust patterns, engineers typically create a scaled-down model of the structure and test it in a wind tunnel. While this was done here with a 150 scale model, the unique topography demanded more drastic research. David Mackenzie elaborates, "What we then did were some localized tests, both physical and computational. We modeled the entire surrounding environment, all the hills, the valleys. This allowed us to calculate the accelerated flows locally, because they significantly increase the net wind speed. For example, if there's a 20% acceleration, your maximum wind speed of say 50 meters per second is now 60 or 70 meters per second. So you have to take those factors into account, and that was the crucial work done here. These specific studies were vital to the design. The ability to stabilize this bridge with an incredibly strong arch is crucial, especially as it stretches over a canyon hundreds of meters above the river below. To actually build it, crews first had to construct a cable crane. It's akin to an aerial trapeze or a monorail made of cables. Towers are erected on either side of the canyon, and a cable connects them. Pieces of steel for the arch are winched across on the cable crane to their correct locations. Each side of the arch is then built from the bottom upwards, held back by cables that are anchored into the rock to prevent it from falling nearly 400 meters down into the river. Once complete, an arch is formed. The arch is the key component supporting the entire bridge structure, but it's not yet ready for a train. Once the supporting towers are erected, the top deck comes into play, a remarkably heavy component. The top deck is a flat section of the bridge constructed in segments. Essentially, working from each side of the canyon, a piece of the bridge deck is laid. Then, another piece is added behind it, and so on, gradually pushing the bridge deck across the canyon until the two sides meet in the middle. This is known as a launch methodology. Intriguingly, the sheer size of this structure means that the scale of earthquakes generally experienced here shouldn't pose too significant an issue for the main arch. But this isn't merely a stroke of luck. Engineers were well aware that this area faces intense seismic activity. David Mackenzie explains, "When you have bridges of this size, curiously, if you imagine the ground is shaking, but in proportion to the size and span of the structure, that shaking is actually quite small. If the span is relatively smaller, that shaking effect is twice as much because the shaking is a fixed amount. So the ground shakes by, let's say, plus or minus 10 centimeters. But if the bridge is 100 meters long, and you double it to 200 meters long, then the relative effect diminishes. So, seismic activity has less of an impact on the main arch, but it does affect all the rest of the approach structures. It goes without saying that the stability of the top deck is paramount. The safety of trains must be central to the project's construction. One of the key environmental threats to the bridge's stability is one experienced globally: sunshine. Temperatures at the Chenab Bridge vary from freezing to a scorching 50 degrees Celsius, and this significantly impacts the steel of the bridge arch. The major problem with the canyon is that the sun can only illuminate sections of the bridge at any one time, meaning it will operate at different temperatures. As the bridge arch warms and cools, it bends and flexes, which is undesirable for moving trains. To counter this, the rails have been pre-stressed, pulled very taut for stability, They are also allowed to move freely within their fixings on the bridge. The rails sit in these fixings but are not actually attached, allowing them to shift back and forth as the bridge moves over time. Designed by the WSP team in Finland, the arch and its towers loom majestically over the Chenab River. The rock and steel blend seamlessly with the mountainous backdrop, offering some of the most spectacular train passenger views on the planet. David Mackenzie reflects, "I've been fortunate, very fortunate, to work on a number of very exciting structures in my lifetime. But this one holds a particular passion for me, because having seen it from the ground up over a 20-year period, having witnessed where it's been built, and the quality with which it's been built, it's incredible how well it's been fabricated in the yard. It really is an incredible piece of engineering, and just looking at the pictures on my screen in front of me, it truly touches the heart as being the challenge I am most interested in. The proof is I have it on my laptop every day to look at it. The line was inaugurated in the summer of last year, marking India's next chapter of connectivity. While the Chenab Bridge is just one part of numerous rail projects across the country, it might be the most impressive. To create this bridge, construction teams had to build where no one else had built before. Yet, through determination and innovation, they transformed it into a reality. More than 20 years after construction first began, following delays and complications, boat journeys and trekking on donkeys, cable cranes and kilometers of purpose-built roads, construction crews found a way. The Chenab Bridge is a perfect example of the hardships faced by construction teams working in some of our planet's most extraordinary environments. The enormous effort invested to create structures like this paves the way for future generations and proves once again what the amazing construction industry is capable of.